Since we're taking these complex numbers to powers, we're going to rewrite them in exponential form. Here's our unit circle in the complex plane. W is root 3 over 2 plus 1/2 I. That's going to put W over here where theta is pi over 6. Z is negative 1/2 plus root 3 over 2 times I. That's located over here where theta is 2 pi over 3. So these are our complex numbers in exponential form. And we note that I has an angle of pi over 2. Let's rewrite this equation, substituting for these exponents. This is raised to the r power, so I'm going to multiply the exponent by r, and I'll multiply this exponent by s. Using our rules for exponents, I'm going to add these two and say that these angles are equal to each other, plus a multiple of 2k pi. We have a lot of common factors in these terms, including pi and I, so let's multiply by 6 over pi times I. So this is our new equation, and we're given in the problem statement that r and s are positive, they're integers, and they're not more than 100. So if r is an integer between 1 and 100, then 3 plus r is an integer between 4 and 103 inclusive. Let's take this equation and factor 4 from the right-hand side. And since 3 plus r is between 4 and 103, we can divide by 4 to find the bounds on s plus 3k. S is an integer, k is an integer, so we're only interested in integers. That's all the integers from 1 to 25. Since s is expressed as some number plus a multiple of 3, let's do casework on the mod 3 residual of s plus 3k. So first of all, s plus 3k can be a multiple of 3. This means s is a multiple of 3. So s is any of the multiples of 3 that are less than or equal to 100. This gives us 33 values of s. Let's find the valid corresponding values of r. S plus 3k must be an integer between 1 and 25, and s plus 3k in this case is a multiple of 3. So it's all the multiples of 3 up to and including 24. That's 8 values for s plus 3k. Taking this equation over here and solving for r, multiplying any of these numbers by 4 and subtracting 3 are going to give us valid values of r between 1 and 100. So there are 8 valid values of r. Together, the number of ordered pairs, any of the 33 values of s can be paired with any of the 8 valid values of r. So that's 264 ordered pairs in case 1. Let's go on to case 2. We'll have s plus 3k is 1 in mod 3. This means s is 1 more than a multiple of 3. S is between 1 and 100, so that's going to be 1 and 4 all the way up to 100. Counting, that's 34 values of s. Let's see what works for r. Again, s plus 3k is an integer between 1 and 25, so we're only going to use the mod 1 residuals up to 25. That gives us 9 values of s plus 3k, so r also has 9 values. Counting in case 2, 34 valid values of s and 9 valid values of r gives us 306 for case 2. Here's case 3. So s is all of the mod 2 residuals up to 98. This gives us 33 values of s. Calculating for r, we'll start with s plus 3k. These can only go up to 25, so these mod 2 residuals end at 23. 8 values of s plus 3k gives us 8 values of r. And we'll count case 3. 33 values of s with any of 8 values of r gives us 264 ordered pairs. Now we'll add these, and the answer is 834. If you'd like me to solve any other math contest problems, please leave them in the comments.